Okay, so last time we talked about measures of center, mean, median, and mode, ways to measure the middle. Now we want to talk about what's called measures of dispersion or spread, how spread out the data is. Let's say that this is a shooting target. We haven't talked about this yet, have we? Okay. I did in the other class. I'm confused now. Having deja vu. So this is a shooting target. Let's say that one person shoots at the target, and these are the hits. And we could measure, where's the center of his spray chart. We measured the center, maybe it would be here. Okay. And the second person fire at the target, and this would be their spread. And if we measured their center, maybe it would be in exactly the same place. Okay. So they would have, in theory, they would have the same average. They would have the same middle or same median. Okay. But the one data is more spread out than the other. Which person is the better shot? Better the green? Yeah, the red one, the second one, is a better shot, right? So we need to be able to measure that, how spread out is your data or how concentrated is it? So one way that we're going to talk about it is, can we measure from each data point how far it is from that middle, right? If we measure all these distances to the middle and then compute that average, the average distance of all the points to the middle, that'll give us some measurement of how spread out the data is. Okay, we won't compute an exact average, but that's what we're getting at. Okay, we're going to try to get something close to that. So the first measure of dispersion is called the range. The range is a very crude but easy to calculate measurement. So a measurement of how spread out the data is, just figure out how far it is from the smallest number to the biggest number. Okay. How far is it from the smallest number to the biggest number? So the range is just the maximum value minus the minimum value. It is not a very good measurement of spread, but it is very easy. And one reason why it's not very good is it's very susceptible to outliers. Where are those outliers going to be if you have them? If you have outliers, where are they going to be? They're going to be at the min and max, right? If you have them, they're going to be either at the maximum or the minimum or both. So that's where you're calculating the range at only. So they're very susceptible to outliers, but it's very quick and easy to calculate. So in this example, the range would be the maximum value, 104, minus the minimum value of 2, 102. Very easy to calculate. May not be very useful, but it is a measurement of how spread out your data is. Okay. So to go from something very easy to something very difficult. So the difficult one is the standard deviation. So we're going to differentiate between a sample standard deviation and a population standard deviation. So that's, one's a statistic and one is a parameter, right? The sample standard deviation has the symbol lowercase s. So lowercase s is the sample standard deviation. And the standard deviation calculates what we just talked about a minute ago, that kind of average distance from the data to the middle. Okay. So I'm going to say it's average distance to the mean. I put average in quotations because we don't actually compute the average formula. we do something similar. So S is about how far you would expect a data value to be from the mean. And the mean is our measurement of the middle. So what if S was 0? What if the standard deviation was 0? So the average distance would be 0 to the mean. What would that mean? Sorry? Wouldn't necessarily mean the mean was 0, but the distances from each value to the mean was 0. What would that mean if all the distances were 0? No? So let's say this is the number line and your mean is here. Okay? Whatever it is. So that's x bar. Okay? And all of your data, the distance to this mean is 0. What does that mean? Yeah, all the values are right here. So every data point is the same value. Okay? So if you had a data set that was like this, right? The average is 2. All the distances from all the points to 2 would be 0. This would have a standard deviation of 0. Okay? So it's always positive or 0. It's only 0 when all data values are equal. The units of measurement are the same, so if your data is in feet, then your standard deviation will be in feet, and others. Large values of S indicate that your data is more spread out. Small values of S means your data values are more concentrated together. And they're concentrated together around the mean, around the middle. So here's the formula. Looks very complicated. But we're going to break it down. So to find this average distance to the mean, we need to know what are the, how far is it from each data value to the mean. So inside the formula here, just this part, right? The x of i's are the data values, and what's x bar? It's the sample mean, right? So to figure out how far is it from each data value to the sample mean, we need to know the difference between them all. So you find all the differences between the data values and the mean, and we square them. The reason why we square them is to get rid of any negative numbers. So if the x value is less than the mean, you're going to get a negative value. If the x value is greater than the mean, you get a positive value when you subtract, right? So if the mean was 3, data value is 2, you subtract them, you get a negative number. Okay? We're going to get rid of all those negative numbers by squaring all those differences. So these differences, we're actually going to call them deviations. These are deviations from the mean. We're going to square those deviations from the mean. And to compute an average, you have to add them up. So that's what that sigma symbol means. You add up all the squared deviations. And then we're going to divide by how many there are, except we make a little correction here. We're going to subtract 1 from that. So instead of dividing by n, we divide by n minus 1. And we'll talk about that later. That's why I put average in quotations, because we're not actually computing average, but it's something close. And then because we have all these squared deviations to go backwards, we take the square root at the end. Okay, and that finally gets us to the standard deviation. So let's do an example. We'll go through it step by step. So we have a survey here. Students in a class were asked on a questionnaire, how many children do you think is ideal for a family? And they're classified by gender. So they're broken up by male and female responses. So if we look at these two, they both have 7 members, both have 7 numbers. If I add up the responses for the men, that's 12, right? 4 times 3 plus 2 is 14. Divided by 7 is 2. So it has an average of 2. And for the women, I have 5, 2, so that's 10. Plus another 4 is 14. Again, 14 divided by 7 is 2. They have the same mean. They have the same average. They also have the same range, because the min and max are both 4 and 0. You subtract those, you get 4. So they have the same mean, they have the same range, they have the same median. Okay, but we can tell there's a difference between the two, right? They're not the same data, there's a difference. We're going to see if there's a difference in the standard deviation. So we're going to do the male standard deviation first. And we're going to do this with a table. So in the first column of our table, we're going to put our data. This is going to be the x's. So this is the data for the male responses. 0, 0, 0, 2, 4, 4, 4. And the mean is 2, right? We already calculated the mean was 2. We added them up, we got 14. Divided by 7 is 2. So the mean is 2. So we're going to first calculate the deviations from the mean. How far is it from each data value from the mean? So the first one, 0 minus 2, is negative 2. Same thing for these two. 0 minus 2 is negative 2. 2 minus 2, 0. 4 minus 2, 4 minus 2, 4 minus 2. So those are the deviations from the mean. Okay, well, what if I just took the average of these? Why use that crazy formula? Why don't I just take the average of these? What happens if you add those up? You get 0, right? You get 6 minus 6. So if you're, the mean is in the middle, right? That's our measurement of the middle. It's going to be about where the middle is. So half of your data values are going to be less, and half of them are going to be more. So when I do those subtractions, about half of them are going to be negative, half of them are going to be positive, about the same distance apart. You just add those together with the way they are, you're going to get something close to 0. That's not what we're trying to capture. We're not trying to capture the strict average of the deviations. We want to know how far is it, like a distance. Now you might argue they should use absolute value. That might be a better way, but this is the way that has been agreed upon. Okay, so mathematicians, statisticians have agreed that this is how we're going to do this. Okay, so the way we're going to take care of the negative symbols is to square them. We're going to square the deviations. So when you square negative 2, what do you get? Positive 4. Let's talk about that just a minute. Stop to the side here. If I take this calculation, negative 2 squared, the negative in front is a multiplication by negative 1. So in order of operations, the exponent takes precedent. So in this one, you have to square the 2 first. It's the negative of 2 squared. So you take 2 squared, it's 4. Take the negative of that. This is actually negative 4. Okay? What we want to do is this. We want to actually square negative 2. So you put that in parentheses. You know, if you're doing this in your calculator, you put it in parentheses. And this means to multiply negative 2 by itself. And that gives you the positive 4. That's where you actually multiply 2 negative numbers together. Yes. So you've probably heard that if you square a number, it makes it positive. That's true, but you have to square, if it's negative, you have to square the negative number and not the other way where you're squaring a value and then taking the negative of it. Okay. And in mathematics, we need both of those. We need to be able to do both of those. We need to be able to square a negative number, and we need to be able to take the negative of a squared number. So that's that's okay. But we just have to know the difference between the two. So that is 4. If you just type that in the calculator, you won't get the right answer there. All right, what is 0 squared? 0. And then 2 squared should be easy. 4, 4, 4. So if we add these up, what do we get? There are 6 4s. 24. Right? 6 times 4 is 24. Okay. So the formula. The formula says to take all of those squared deviations and add them up. And that's what we did in the last column. Right? We found all the squared deviations, and then we added the column. So that's the numerator of the formula there. So we've done this part. We figured out that was 24. Okay. That's the hardest part, is getting that sigma number, the sigma x minus x bar squared. Okay. You make a table. You have to find the mean first. Subtract every data value from the mean, or the mean from every data value. Square all those differences, and then add them up. Okay. And then we have n minus 1. Let's just first, what is n minus 1? N is how many data values you have. So how many do we have? 1, 2, 3, 4, 5, 6, 7. So 7 minus 1 is 6. So it's 24 divided by 6, which is what? 4. Square root of 4 is 2. So that's the standard deviation. It's 2. So let's talk about why is it n minus 1. In our data, the mean of this is 2, and we have a data value that's actually equal to 2. Right? So when we subtract the mean from itself, we get 0. All the other distances from the mean in this example are exactly 2, right? They're all 2 away in distance, right? That one's 2 away, 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 that one's 2 away. That's the standard deviation. That's how we should think of the standard deviation. It's how far away, on average, the data values are from the mean. So if we had included the 0, then we would be dividing by 7, and we won't get 2. right? When we find the standard deviation, we'll have 24 divided by 7. Right? So dividing by n minus 1 eliminates the fact, or eliminates the data point that's closest to the mean. Kind of take that one out. You don't really, you're looking for the deviations from all the data points to the mean, not from the mean to itself. Okay, so you're just taking away that one value, and it just gives you a more accurate representation of what you're trying to figure out. How far is it from all the other points to the mean? You don't care about the mean itself. Does that make sense? Okay, so that's why it's n minus 1. And then since we squared all these, we have to take the square root at the end. So that's why we do the square root at the end. The square to get rid of the negatives, the square root at the end to back that out, to go backwards. And that is sample standard deviation. So this a little bit complicated. What if we had 1,000 of these? Be difficult to do this by hand, but people have done it. Okay. That used to be people's jobs, for to just do these calculations. So if we have a lot of data values, we have to use software. Okay. So what I want us to do is open up StatCrunch. And we're going to put both of these data sets into StatCrunch. So the male and the female responses. It's like that. And I'm going to name them too, because help me keep it straight. So I open up StatCrunch, I put the male responses in one column, the female in the other column. So we know the standard deviation for the men, it's 2. Let's make a prediction for the women. Do we think the women data is closer or more clustered around the mean or further away? More clustered around the mean, right? Because all those 2's that are, and the mean is equal to 2. So we would expect the standard deviation to go down for the women column. Okay, I don't know exactly what it is until we calculate it. But I'm going to predict that it's less than 2 because that data is more clustered around the mean. So we're going to go back to this stat, summary stats. This is what you use to find the mean, median, and mode, or mean and median last class, right? Summary stats columns. You pick the column, and you can actually pick both of these. So the way to pick a second one is to hold down Control on your keyboard and then click on the women as well. Okay, so you hold down Control to do multiple selections. Okay, and then we'll compute. So it'll give you 2 rows of statistics. So first row is for men, second row is for women. And we see that our standard deviation for men was 2. And for women, it was 1.15. So it was lower, okay? Anybody need help with StatCrunch? So you go to Stat, Summary Stats, Columns, select the men, then hold down Control on the keyboard, hold down Control, and then select women as well. Hold down Control keys right there at the bottom, yeah. And then click women, and then you'll get both of them. There you go. And click compute. There you go. Anybody else? How do I got what?
The data.
I typed them in.
Oh, okay.
Yeah, one by one. Yeah. All right, so leave that data there. Don't close that window. We'll go back to that. So population standard deviation has a different symbol. It's also called sigma, but it is the lowercase sigma in the Greek alphabet. So that's what this guy is. Lowercase sigma. The uppercase looks like that, right? That's our sum symbol. The lowercase is this little, it looks like almost like an R, but it's like a fat R, okay? Or a circle with a tail on the top. The population standard deviation has the same formula, except we find deviations from the population mean, so that would be mu, instead of x bar. I told you had to know the symbols, right? So instead of x bar, we're going to take deviations from mu, and we divide by the population size, n. We do not subtract 1 here. The reason is your population sizes are usually so large that subtracting 1 doesn't do a whole lot to the calculation, so we just throw it out. Okay. The sample standard deviation, the n minus 1 helps you get that sample standard deviation closer to the population standard deviation. But when you're calculating the population standard deviation, you don't subtract 1. Okay. So in StatCrunch, in my output here, I just have this standard deviation. But we know that, we calculated our standard deviation and got 2. We calculated the sample standard deviation. So if we wanted the population standard deviation, that's not it. So this default standard deviation in StatCrunch is the sample standard deviation. It's using the sample standard deviation formula. It's dividing by n minus 1 instead of n. Okay. So how do we get the other? I'm glad you asked. So click Options and Edit. So we're going to go back to this menu where we pick the columns, men and women. And down here we have a list of statistics. These are the ones that are highlighted are the ones that are defaulted for you already, but you have others. And if you go down, there's one called unadjusted standard deviation. Unadjusted standard deviation. That's going to be the population standard deviation. I'm just going to add it on to the end by holding down Control and clicking on that new one. And it's just going to add it to my list. It adds it to the list on the right side. Okay. So and you can see here it's added to my list at the bottom. The n minus 1, the minus 1 on the sample standard deviation formula is the adjustment. They're making an adjustment to make that calculation a better one. If we want to not use that, we use the unadjusted standard deviation. That's going to be the same as the population standard deviation. I wish that StatCrunch just called this population and the other one sample, but that's not what it does. Okay. So if we want to use StatCrunch, we have to deal with the way it is. and it calls the standard deviation the sample, or wrong way. It calls the sample standard deviation just the standard deviation. It calls the population standard deviation the unadjusted standard deviation. So if we click compute, and I'll need to scroll over to the very end, I get the same thing except they've divided by 7 instead of 6 in that calculation. Yes? You clicked on it? Let's just see. Oh, you gotta have one of these. It did do it.
It did?
It didn't do it.
Oh, it didn't.
Let's see. So you got a Mac, right? So your control is different.
Yeah, that's what I was thinking.
Yeah. So I don't know which one it is.
It would be command, probably.
Command. Let's try command. Yeah, that was it. Thank you. All right, so if you're using a Mac, instead of holding down control, you're going to hold down command if you have a Mac. So let's just verify this. So if I took the square root of 24 divided by 7, that should be the population standard deviation if we treat this like a population. And we get the 1.85. So that's correct. Okay, so instead of dividing by 6, we divided by 7. So you have to be careful in your homework if it asks for the population standard deviation, you have to use the unadjusted standard deviation, okay? Or you will not get it correct, and you will get very frustrated, okay? So make sure that you're using the right thing. And it might not say population. It might just say find sigma. And you just have to know that sigma means, the lowercase sigma means population standard deviation, which means unadjusted standard deviation in StatCrunch. Okay. The variance is another measurement of spread, and it is the square of the standard deviation. It's the square of the standard deviation. So the sample variance is S squared. So that's the sample variance. So S is the standard deviation of the sample. So if I take the standard deviation and then I square it, what happens? If you square a square root, what does that do? You square a square root. So here's the square root of 4. That's 2. Right? If I square that, that would be the square of 2, right, which is 4. So if you square a square root, they cancel each other out, right? They're opposite operations. They're doing the opposite things. If I square 2, I get 4. Take the square root of 4, I get 2. They reverse each other, right? So the square root symbol just cancels out for the variance. So the variance is just this part. It's that part that's under the square root, you know, when you're doing the calculation by hand. So before, let's go back to here. What's the variance for this one? It's just 4, right? So it's this part that's under the root. Also, if you already know that s is 2, so if s is equal to 2, then s squared would have to be 2 squared, right, which is 4. You could just square the standard deviation, you'll get it. So that's called the variance. So if the standard deviation is the average deviation from the mean, then the variance is the average squared deviation from the mean. So it's just another measurement. And it's one less step to do if you're doing this calculation by hand. You don't have to take the square root.
Go back to that slide.
Yep. I need to add to this. So sigma squared would be just this part, right, without the square root, because the square and the square root cancel each other out. Yeah.
So, sample
Population,
population is
lowercase sigma.
sigma 10
So for S, you are subtracting the sample mean, and you're dividing by n minus 1. And with population, standard deviation, sigma, you're subtracting the population mean, and you're just dividing by n. You're not doing the subtract 1. The means are calculated exactly the same way. So the only real difference when you're doing the calculation is for the sample, you subtract 1 on the bottom, and for the population, you don't. Yeah, that's the only difference. And the difference will be, at the beginning, you'll have to decide which one it is. So if I'm doing this for a sample, I have to use S. If I'm doing it for a population, it has to be sigma.
What does the m mean?
That's mu, it's population means, the mean of the population, which is our center. And we're finding average to the middle. That's how we're calculating the middle, it's the mean. And X bar, I know that doesn't look like an X bar, but that's an X bar. That's the mean of a sample. So in our StatCrunch example here, I'm going to go to Options, Edit, and I'm also going to add the unadjusted variance. So if you need the population variance, you want the unadjusted variance. So I'm just going to add that on to my list. And I'll get both of these. So when we did that table by hand, we got a standard deviation of 2 and we got a variance of 4. That's what StatCrunch says it is as well. Okay. For the if we treat it like a population, though, the unadjusted standard deviation will be the correct standard deviation, so it will be a little bit less, 1.85, and then the variance is the unadjusted variance if you're treating it like a population. Now, our example was a sample, but if you treat it like a population, you're going to use the unadjusted versions in StatCrunch. And then we have the same for the women responses, and you can see they're both smaller because that data was closer to 2, which was the mean. Any questions? I know you have questions. It's the first difficult thing we've done. So feel free to ask. Yeah.
Sample would be standard QE. That's what you plug into the that section on StatCrunch.
If it's a sample, it's the default standard deviation in StatCrunch. You know, if we just started over, when I went to stats, summary stats, columns, it defaults to give me this list of things to calculate. And the standard deviation is one of those. And that is the sample standard deviation is the default. And the variance it gives you is the sample variance. That's the default. Okay? You're usually dealing with sample data. You rarely have population data. But if you did, then you would use the unadjusted versions instead if you have a population. Okay? If the data you have represents a population, then you use the unadjusted versions. Okay? But most of the time you're taking a sample because populations are hard to get. Right? But your homework will specifically ask you to do one or the other, and you got to know which one to use. Okay? Okay. How about before we do this, let's see if we're all on the same page. We have this data set. I think it's the same one we used last week. I want you to find the standard deviation, and you need to find the correct one. And you have StatCrunch. Hint, hint, wink, wink. All right, let's see what you guys think. So most of you say A. At least one person said B. Correct answer was A. So, good in StatCrunch. Let's see if I can do split screen here. In StatCrunch, just in a column, I don't really care which one. I got my data in, stats, summary stats, columns. I pick that column. It's a sample. And there's my sample standard deviation. And the answer choices were all rounded to 1 decimal, so it was 5.7. Does anybody have a question about that? What does that 5.7 mean? Right, it's the average distance that your data points are to the mean, which is your calculation of what the middle is. So our mean is 9. So you're saying of these data values, right, your typical distance from each data value to 9 is 5.7. Okay, that's what that standard deviation means. Okay. Okay. So next is the range rule of thumb. I'm going to display the screen now. We might be done with StatCrunch for a little while. This might make it easier for you to see. So the range rule of thumb is a way to categorize your data into usual and unusual data. So we're going to say usual data values are within 2 standard deviations from the mean. So that means any data value that's no further away from the mean than 2 standard deviations, we're going to call that usual. Anything outside of that, we're going to call unusual. So we're getting closer to that definition of what an outlier is. This is not the definition of outlier, but it's kind of close. So we're just going to say usual, unusual. Usual, you're close enough to the mean that you're within 2 standard deviations, and unusual if you're outside of that. So in 2002, it says the mean weight for American males ages 20 to 74 was 191 pounds. Assuming a standard deviation of 26 pounds, would an American male weighing 240 pounds be considered to have an unusual weight? So this says in 2002 the mean weight for American males was 191. That's telling you that the population mean is 191, not 199. Messed up there. 191. Okay? And it has a standard deviation of 26, so that means sigma is 26. That's the population standard deviation. So any weight that's within 2 standard deviations of 191 is going to be called usual. So what is 2 standard deviations? Well, 1 standard deviation is 26, so what's 2 standard deviations? 52. So any weight that's within 52 pounds of 191 is going to be considered usual, and anything outside of that is unusual. So we're going to calculate this using a little formula. So the minimum usual value would be the mean minus 2 standard deviations, and the max usual value would be the mean plus 2 standard deviations. That's going to be above or below the mean by 2 standard deviations. So mu is 191, and sigma is 26. That. So we just need to calculate those two. And look how I typed that in the calculator. Exactly the way I wrote it down, okay? Your TI-84 will figure out the order of operations and all that. So that's 139. 191 plus 2 times 26. 243. So this means any weight for an American male between 139 and 243, we're going to say that's usual, and outside of that is unusual. So would an American male weighing 240 pounds be considered to have an unusual weight? The answer is no. Because 240 is between those two. Okay. So that's called the range rule of thumb. So the rule of thumb is anything within 2 standard deviations of the mean is considered to be usual. Anything outside of that is unusual. Okay, this is called the empirical rule. So this is very similar to the range rule of thumb, except we're going to include there's this extra condition that it has to be a normal distribution. So if you have a normal distribution, we know about how much of our data is within so many standard deviations from the mean. So the first empirical rule is that if you have a normal distribution, about 68% of your data will be within 1 standard deviation of the mean. In the normal distribution, your mean will be right in the middle. It's symmetrical. Your median too. Your mean and median will be right in the middle of your data. So this is the population mean mu. And then 1 standard deviation more than the mean would be mu plus 1 standard deviation. Mu plus 1 sigma. And then 1 standard deviation less than the mean will be mu minus sigma. So if the mean was 100 and the standard deviation was 15, then this would be 115 and this would be 85. Does that make sense? If your mean is 100, your standard deviation is 15, you just add 15, subtract 15. That gives you a range where you're within 1 standard deviation of that mean. Okay? So the rule says 68% of all your data will be there because it has, the height of this is the frequency, right? It's like a frequency. It's not a histogram, but it looks like it's like the histogram. So its frequency is how tall it is. So the most of your data is concentrated around your mean. So 68%. And because the mean is right in the middle and your normal distribution is symmetrical, we know that we can divide that 68 by 2 and know that there's 34% in each piece. There's 34% from the mean to 1 standard deviation more, and there's 34% from 1 standard deviation less than the mean up to the mean. So it turns out that IQ scores have a mean of 100 and a standard deviation of 15. Okay? So that's just based on historical data. Okay? So what this tells us is that we know that 34% of the population will have an IQ between 100 and 115. Well, 34% of our population will have an IQ in that range. And 34% will also have an IQ between 85 and 100. So we'll have another 34% that'll be just here. And 68%, which is, over 2/3, will have an IQ between 85 and 115. Okay. And to have an IQ greater, right, the frequencies drop down, or less, the frequencies drop down. It's more unusual to have them, off to the right or to the left. The second empirical rule says that 95% of your data is within 2 standard deviations of the mean. And remember that 2 standard deviations means that they're usual. But the range rule of thumb says anything within 2 is usual, anything outside of that's unusual. So 95% of our data will be usual. That makes sense, okay? And then the other 5% will be the unusual. Okay? So if this is 95%, that includes the 68, right? The 68 is part of that 95%. So what are we adding on if we take 95 and we subtract 68? We get 27%. So adding that extra standard deviation on each side adds 27%. Divide that by 2, you get 13.5. So that's where this 13.5 comes from, here and here. So 13.5 in each of those little pieces. Okay. And then if you go out to 3 standard deviations, the rule is 99.7% of your data will be within 3 standard deviations of the mean, which is almost all. It's not all, though. It's almost all of it. Let's see here. So 2 standard deviations would be 130. This is 145. This would be 70, and this would be 55. Okay. So 3 standard deviations would go from 55 to 145. That says 99.7% of our population has an IQ between 55 and 145. Does that make sense? Yeah. I mean, that's almost full range. There's going to be very few people that have an IQ that's not in that range, 55 to 145. Okay. Of course, my IQ is way out here. I mean, you can't even see it on the graph, but, I'm just kidding. But you're adding how much percentage when you go from 95 to 99.7? We'll just subtract them. 99.7 minus 95 gives us 4.7%. Divide that by 2, that's 2.35%. So that's where this 2.35% comes from. Here and here. Just that little piece has 2.35% of our population has, 2.35% have an IQ between 130 and 145. Okay. And then we still have some left over on the outside. Within 3 standard deviations is 99.7%. So what's left? 0.3%. Right? 100% minus 99.7 would be 0.3. So there's 0.3% left on the outside. And if you divide that by 2, you get 0.15% in each of these pieces. Right? Okay. There's some good news and bad news. Right? The bad news is I'm going to make you draw this on the test. You have to draw this picture. Okay. The good news is that you have this generic template on your formula sheet. Okay. All the percentages on it. Is take your data, your mean and your standard deviation. You have to fill out these. Right? What's in the middle, and then count off standard deviations to the left and right. And then you can answer questions. Okay. So we're going to answer questions about this data. The standard deviation?
Yeah.
No.
So how'd you find that out? I bet it was 15.
I knew it.
Is that where your IQ comes in?
I knew what the standard deviation of IQs is. Just from, I read it. But in your problem, it'll tell you. Yeah. So this one's going to tell us. It says, given a data set with a mean of 45 and a standard deviation of 3, what percentage of the data is between 39 and 54? We need to add something here. Assume the data is normally distributed. We have to have a normal distribution for this thing to work. Okay. We have to have that bell-shaped curve for all those percentages to work out. And just remember that those percentages are approximations. Okay, they're not exact. Okay, it's our best guess here. So what we're going to do is we're going to start out with this 45 and 3, and we're going to draw. This is what you're going to do on the test. You're going to draw that normal distribution. So you need a number line. You're going to draw the bell. If it's a bell, it's not a cup or anything else. It's not a V or a U. It's a bell, which means you have to kind of curve up and then curve down and then curve up like that. Okay. None of this stuff and not that. Okay, it's not either one of those. It's got this shape. And it doesn't have to be perfect. Doesn't have to be great. It just needs to look sort of like it's supposed to look. Okay. The mean goes right in the middle, so we're going to put 45 in the middle. That's our mean. The standard deviation is what? 3? So I'm going to mark off standard deviation to the left and right. 48 and 42. Right? I'm just going to add, subtract, and try to keep it symmetrical. It doesn't have to be perfect. You're just going to use it to figure out your problem. Okay? It doesn't have to be perfect. And then 2 standard deviations. So we're going to add and subtract another 3. So that'd be 51 and 39. And then we're going to do it one more time. 54 and 36. And we're going to use the picture, the template, to fill out all the percentages. I have them memorized, but you can use the template that's on the formula sheet, and it's in your notes. So if this is on the test, it's going to say you have to show your work on your paper. That's what you're going to draw. Okay, you're going to draw this on your paper. And then you're going to do any other calculations there with it. Okay. So the first question is, what percentage of the data is between 39 and 54? Okay. So from 39 to 51 is what? That's 2 standard deviations, right? That's 95, right? That's one of our rules. It said, well, that's 95. And then we add this extra piece here. all the way to 54, we're going to add 2.35. Now you could just add all these percentages, 13.5, 34, 34, 13.5, 2.35. But I already know what this is. That's 95. So 95 plus 2.35. Okay, what about between 45 and 51? So that's these two, right? It's those two together. So that would be 34% plus 13.5%. So 34 plus 13.5, 47.5%. What about less than 42? That would be all of these, right? It would be these three added together. So 0.15 plus 2.35 plus 13.5. 16? You check that, make sure that's 16. I think it's 16. Any questions?